Okay, it seems like most folks have been able to join us. Yeah, thank you again for joining us for the California Fire Science Seminar Series. We're going to go ahead and get started. So my name is Nick Dutch. I'll be your host today. I'm a member of the student committee who assisted in organizing the California Fire Science Seminar Series. I'm currently completing my geospatial master's degree at UCLA, and I also work as a staff research associate with the UC Cooperative Extension's post-fire forest resilience program up in the Sierra Nevadas, and I'm based in Quincy, California. The California Fire Science Seminar Series is organized and supported by the California Fire Science Consortium, the Fire Research Group, the University of California, Berkeley, and the University of California, Merced. The student committee was an integral part to the success of the seminar series, which included 12 students and postdocs from across the nation who helped select these speakers and topics for the series. This webinar is going to be recorded and will be posted on the California Fire Science Consortium website and YouTube channel. And following today's presentation, there will also be a Q&A session. So please feel free to add any questions you have to the Q&A chat throughout the presentation, and then I'll be moderating those at the very end. So today's seminar is a framework for reconstructing pre-Euro-American fire regimes in California. Will be presented by Dr. Andrea Duane. Dr. Duane is a postdoctoral researcher at UC Davis whose work focuses on quantifying changes in fire regimes, understanding their driving mechanisms, and assessing their impacts on ecosystems. She earned her PhD at the University Autónoma de Barcelona and received the 2025 Award for the Excellence in Postdoctoral Research from UC Davis. And thank you, everyone, and please welcome me in joining Dr. Andrea Duane.
Thank you, Nick. I'm going to share my screen. Can you see my screen?
Yes, everything looks great.
Okay. Well, thank you, Nick, and thank you, everyone, and especially for the folks from the California Fire Science Consortium for inviting me to being a panelist in this fantastic series. I'm honored to be the first one here today. Today I'm going to talk about a framework for reconstructing pre-Euro-American fire regimes in California. Let's see if technology helps here. Yeah. So recent wildfire trends in California are worrisome. In the last 23 years, we have seen an increase of 15 times the amount of burned area. Also importantly, carbon emissions have also increased tenfold, linked to an increase not only in burnt area, but also in the higher severity fire area burned. However, it's interesting to know that these patterns are usually below the historical baselines. According to some historical articles like Stephens 27, Martin and Such 1992, and a new paper that it's under preparation, we estimate that the historical burnt area was between 1.3 and 2.3 million hectares at the whole state. Since the year 2000, we have only reached this amount of burnt area one time, which was in the year 2020. So California fire regimes are changing at an increasingly rapid pace, leading to ecosystem degradation and increasingly risky conditions for humans. Among the most important impacts on ecosystems and humans are increasing smoke from giant wildfires, ecosystem impacts of changing fire frequencies, like for instance, too little fire in mountain forests and too much fire in SoCal or Great Basin or near urban areas. And also we know that conifer forests are having trouble in recovering from large and severe fires. To face this problem, documents like the California Carbon Plan and the California Wildfire and Forest Resilient Action Plan are setting ambitious goals for forest treatments, including prescribed fire more than 40,000 hectares per year at the whole state, or in recent plans, they are talking about more than 100,000 hectares per year for the year 2045. So effective science-based responses require a strong foundation of evidence of the drivers and patterns of ecosystems. As the use of fire as a management tool expands, as we see, it is critical to demonstrate its ecological benefits, while at the same time carefully considering some trade-off. One very important in prescribed burns are smoke emissions. However, a key step of addressing this challenge is establishing the baseline conditions that existed before the Euro-American settlement. In this case, we consider before 1850. This is not just to get a baseline or a photo of the past, it's also to comprehend the temporal dynamics of ecosystem processes and patterns, also to recognize and understand the nature and impact of human interactions with ecosystems, and refocus management efforts on critical ecosystem processes rather than just conserving ecological, specific biological players at a time capsule, like for instance, one single species. So we want to use this kind of history as waypoints rather than just endpoints. So the goal of this lecture is to provide a framework that reconstructs historical fire regimes in California. And to do so, there are two main questions we want to answer. First of all, what type of vegetation covered California? And then how often did this vegetation burn, and what were the associated emissions of these fires? So first of all, I'm going to start with the historical vegetation map. The overview of the method behind the reconstruction of the historical map is the one represented in this diagram. I'm going to, in the following slides, be explaining each of the items presented here, but first of all, I will be explaining the base map that we are using, which is the VPS, and then how we are introducing some very good historical maps that reconstruct historical vegetation, how we are also including long-term present evidence of vegetation patterns, the indigenous impact, and also some present data that is also important to try to understand how the past was. Our approach is based in using the biophysical settings vegetation layer from the land fire projects. I'm pretty sure that a lot of you are familiar with the land fire program. One of the layers they have is this biophysical vegetation layer. This is their version for 2020, which is, I think it's the most up-to-date version. This BPS product represents at 30-meter spatial resolution the vegetation systems that likely dominated the landscape prior to Euroamerican settlement. And it's based on modern biophysical environment and model pre-European settlement fire regimes. There are 118 VPS vegetation types in California in this map. These types are linked to quantitative disturbance succession models, which are synthesized and descriptive documents that provide ecological information about ecosystem dynamics, structure, composition, and disturbance regimes. At this time, this map is the only map of potential vegetation in California that is based on a transparent and peer-reviewed modeling process. So this is the base for our work. But first of all, we crosswalk these 118 types into 38 what we call PFR or pre-settlement fire regime types. 28 coming from Vandenwater and Safford 2011, and then added new ones. These PFR types are like broad and easily recognized vegetation types that are defined based on their natural fire regime. So each type has shared fire regime attributes. So all the VPS types are based on pre-European fire regimes. The map is modeled based on modern plots and modern climate. What happens is that late seral stages of vegetation dominate the landscape, but this assumption fails in parts of the US where frequent or widespread anthropogenic burning maintain early seral conditions. So what we see here is that there's an underprediction of grasslands and other herbaceous vegetation in California, where pre-Euro-American population was high. Also, we see that if you look at the Central Valley of California, all these like bluish, greenish areas are it's all riparian vegetation in the northern part of the Central Valley. And then you have a lot of shrubland, which is more this like yellow-orange color in the southern part. And we have a lot of evidence that the Central Valley look very differently. However, the Central Valley per se, it's very challenging because current land use conversion, like agriculture and urban expansion, hinders a proper modeling of the historical vegetation here. So now that we have a base layer, what we are going to do is to introduce very good products that are out there, historical maps of different parts of the state. First of all, the Central Valley Historical Mapping Project from California State University at Chico in 2003 maps historical vegetation in the pre-19, they call pre-19th century, and also 1945, 1960, and 1990 part-time periods. The work uses journals, diaries, newspaper articles describing historical conditions, early maps, surveys, aerial photography, landscape photography, sketches, and paintings to reproduce historical vegetation. Just as a curiosity, I found that they used 700 maps were scanned to build this map and have this common legend across the whole valley. However, in some areas, this map is a bit coarse in terms of the spatial resolution on like the mosaics that they create. So we also use other sources. A very important source is the one that has been delivered by the San Francisco Estuary Institute. This institute has a huge effort to provide reconstruction of historical conditions in some areas around the Bay Area to help restoration strategies. Among the data generated, they have a reconstruction of the 18th century map that represents vegetation of the region. In this case, you can see here the Sacramento-San Joaquin Delta area. And it also includes this tidal vegetation. So it's kind of a really, really nice product here. If you have time, it's worth having a visit to the story maps they have in their website, in this arrow that I added here at the bottom called A Valley Shaped by Water, in which they explain in very detail all the steps that they use to reconstruct this map, as using, for instance, journals, diaries, newspaper articles, early maps, surveys, photography. I mean, very similar to the one before, but it's a really, really nice product that they have. And they not only have this area, they also provide many other areas, like, for instance, Alameda Creek, Laguna de Santa Rosa, South Santa Clara, Ventura County. I mean, there's plenty of areas with these maps. I mean, wish I could have for the whole state, but in these areas that we have it, what we decided is just to overlap these maps on top of the BPS maps. We also have some more like hidden products, which is in this case the Tahalil lead to ill master thesis in the Pewter Creek area, entitled A Historical Ecology of the Cache Pewter Creek Alluvial Plain in the Sacramento Valley in California from 2019 at UC Davis. It provides a comprehensive reconstruction of vegetation in this area, which is like western of Davis and Woodland. And it uses, again, public land surveys, soil maps. I mean, you have here a timeline of the different sources of each of the different years, with aerial photograph, even paintings, and all these different sources that help to reconstruct all this area. So again, we overlap this map. Well, in this case, we didn't have the GIS product, so we did a tough work of georeferencing and reconstructing this in a GIS map so we could add it in our work. The Tulare Basin map developed by the Stanislaw Endangered Species Recovery Program at California State University, done by Scott Fillings, it's also a very interesting product that reproduces historical landscape conditions in the Tulare Basin and also in the San Joaquin Valley. Again, it uses similar sources like early irrigation maps, historical topographic maps, literature, but also geologic, physical landscape data, and carbon vegetation sources to reproduce historical vegetation data. There's a overlap with this map and the Chico map that we saved, which is from the California State University of Chico, but we believe this one provides a better resolution. So in the cases where we had this map or the San Joaquin Valley map, we are using this map, but for the Sacramento Valley, except for the other maps I showed before, we are using the Chica map. And then we also have included a historical reconstruction of the San Francisco city area. If we look at the left, we look at the BPS map, we see a funny representation here because according to this map, the Golden Gate Park had a different vegetation than its surroundings in historical vegetation. And that's an artifact from the modeling process. But then there's this project called Hidden Nature in San Francisco that they partnered with the San Francisco Estuary Institute, and they combined dozens of historical maps, photos, illustrations, and documents to reproduce how San Francisco looked like before the construction of the city. So again, we overlap this map to our map. These were like all the different historical maps that we use to improve the mapping, but then we also have this long-term evidence, which is the phytolith data. Phytoliths are microscopic structures of biogenic silica, which you can see here at the bottom, at the top left of the slide. And the vegetation composition is the dominant driver of sulfitolith content. This phytolith content is consistently higher in soil under persistent grassland compared to other vegetation types. So soils with phytolith contents above 0.3% were likely dominated by native grasses for centuries or millennia. In this very interesting work from Fick and Yvette 2018, they generate a California map of sulfitolith content using 120 plots and different environmental variables and species distribution model to reconstruct the soil content. And then from this, we can get where grasses were very likely present before European settlement, which is this map in the right. And then we have a big chapter, which is the indigenous impact on vegetation maps. It mostly depends on historical population location and the impacts on vegetation. Prior to widespread Euro-American settlement, Native Americans exerted a profound influence on vegetation through much of the state, with fire being the most prominent and important management tool. Indigenous people commonly use fire to maintain more open grass and forest-dominated habitats in areas with the highest densities of people, in particular near village sites and along trail networks. Indigenous people commonly use fire to maintain more open grass, to forest-dominated habitats, and to inhibit encroachment of dense woody vegetation for many reasons, as I'm sure lots of you know, but like safety, resources, ease of mobility, and so on. So vegetation type change is needed in intensely managed cultural sites in order to represent historical conditions. And the VPS, as I showed you before, often assigns shrubland or forest vegetations to locations where human activities had previously maintained grasslands. So this is why we need a methodology to include this effect on the VPS map. And how were we going to do it? We're going to, first of all, need to know where this impact happened. We need maps. We need maps, especially maps of villages. So first of all, we got this general overview of the tribal groups of California. And for each of these groups, we thought, well, maybe there's information out there that represents the distribution, spatial distribution of villages. And this information was out there, actually. As you can see here at the right, this is a map for the Patwin people in Central California by Crover 1932. And apart from the general topology, topography and hydrology, there are several places where villages are mapped. So what we did was we took many, like dozens of maps, like this one here or these ones that I'm showing right now. So we did this for most of the 52 groups that I showed in the slide before. In this, here I show two examples. In the left, you can see the Yuki people. From this map comes from the Handbook of North American Indians, and you can see all these different black dots are the villages in this area here. And this is a very well-known representation of the Chumash people near Santa Barbara. Sorry, the Yuki people are in the Coast Range Mountains. And this, on the right, you can see the Chumash people near Santa Barbara. And this maps also represents villages all in this area. So I took these maps, I georeferenced them, and then we located each of these villages for all these different groups. We use extensive reports that are out there for the Chumash, for the Namlaki, for the Shastan, for the Achumawi, for the Patwinans, for the Sumek. For all of them, we have specific reports. And then we have a lot of maps coming from the Handbook of North American Indians, for many of the Indian groups. And then for other ones, we took the Atlas of Western Prehistory from Winslow and Wilson 2022, in which they also have a very interesting map of villages in California. We also digitized the statewide trade network from Davis 1961. This is our author that draw the Indian trails of Aboriginal California. So we also digitize all these networks that you're seeing here. So the results are that we had maps of 14,000 kilometers of trails and more than 2,000 villages across California. What we believe it's certainly an underestimate of the number of villages. Why? Because first of all, there are some areas that are like blank areas, few of them, but we had no maps. And also because we think that the mapping products are not exactly in the same quality everywhere. This is an example here. The left side, you can see an area around Oroville. Each of these blue dots is a village map. This area covers 85,000 hectares and includes 85 villages, which is, yeah, it's kind of a high number of villages. And if we take a similar ecoregion, but southern of this area, which is East Sacramento, and we have an equal surface. This area includes 19 villages. What we think is that it's not because there were less villages, but the mapping method or effort was not exactly the same. So we believe we are missing part of the story if we only take the villages that were actually mapped from all these different sources. So we have a challenge is if we want to really reproduce indigenous impacts on vegetation, we need to have enough good product to model this impact. So we wanted to have a way to inferring the location of missing villages. This area is the Chumash people area near Santa Barbara. The blue dots are the actual villages that were mapped. And then we did an exercise of allocation of new villages according to a machine learning model. How many? This was more like a top-down approach. We used the historical population value in California. We merged different sources and we had an average. And according to different village sizes, we inferred how many villages were supposed to be in California, which was like around 5,000. And then we included this amount, like missing villages in the country, but for different ecoregions and different sizes. So village sizes was included. As a predictor variables, we use distance to streams, digital elevation model, and the original BPS because we needed some kind of guidance on the main vegetation types. And we also had some validation values. This is the AUC is a performance value. It ranges between usually like 0.5 is not a very good model and 1 it's a perfect model. In our case, these models range between 0.757 for an area around the Mojave Desert, which was kind of challenging to model, and then up to 0.82 for the Sierra Nevada area. Okay, now that we have the villages, we need to assign an area of influence around the villages. So we decided that the typical, according to conversations with a lot of experts, that the typical area of influence of highly impacted by indigenous management was between half a day and 1 day walking from each village, which in this case we considered it could be like either like 4 kilometers or 8 kilometers, which is up to 5 miles more or less. So we built these buffers around each of the villages. We use a negative Gaussian buffer with a soft randomized cutoff at the end. So we kind of try to mimic more natural patterns that vary strict limits. In each of these pixels, like these yellow pixels around of the villages, we applied kind of a backwards succession conversion. So it was only applied to certain vegetation types like shrubs or mixed evergreen that we know according to literature that these are typical vegetation types that come from the encroachment of early stages of vegetation. And once we decided that these pixels were going to, also we applied a topographically dependent decision. So if these vegetation types like shrubs were occurring in bottom valleys, these were not going to be back to converted because also according to meetings with experts, everyone agreed that the landscape was very heterogeneous and there were a lot of grasses, but also a lot of areas with shrublands. So we decided to keep, like for instance, chaparral in bottom valleys. And also apply different rules according to slope and aspect, and you will see this further on. So grasslands were assigned more in southern slope in contrast to eastern and western slopes. And the new grasslands types, once this pixel was decided to be converted, were assigned according to climate and topographical features, especially distance to the coast and elevation. So if it was in the coast, this grassland type was going to be coastal prairie, and then in other places more like a mountain meadow, or in other places more like typical Californian grassland. And this is a way we included indigenous impact on the mapping. And then I also going to explain how we are using present data also to improve the VPS. Red fir areas, we believe, are overrepresented in the VPS in regards current vegetation maps. In the top right image here, you can see the VPS near Lake Tahoe, and all these red areas are red fir areas. But we know that red fir is relatively fire sensitive, and that a century of fire suppression has probably increased the extent of red fir in the Sierra Nevada, not decreased it. So the current distribution that we have nowadays, it should be like the maximum distribution if we understand the successional patterns. So what we decided is that we conserve the pixels of red fir that were coincident both in VPS and FVEG, which FVEG here is kind of the current vegetation map, is a product from Frapcal fire. So these areas were conserved as red fir. For the rest of the areas that VPS was mapping as red fir, we added the vegetation type that FVEG is mapping the current vegetation. That's the solution we decided to follow. So this bottom right is our map after this modification. On the contrary, the yellow pine forests are widely underrepresented in VPS as compared to current vegetation maps. At the top right image here, you can see an area around Shasta Mountain, and you can see the VPS is mapping different, like red fir or mixed evergreen. But there's a big area here in the middle that is not including yellow pine. But we know that yellow pine forests are commonly maintained by frequent fire, and current landscapes have largely been shaped by prolonged fire suppression. Historical distribution of yellow pine was certainly more extensive than it is today. So the current extension of yellow pines actually represents a minimum baseline. So we extracted the areas of yellow pine from the current FVEG map and added them to the VPS map to improve this fact. And finally, we also included serpentine vegetation. So in the VPS, as you can see here, this is in Western California, and VPS maps some serpentine vegetation, which is this purple areas that you can see at the left part of the map. But they are under map because the very coarse geological layer using the VPS mapping process. So we overlaid the California State Geological Map and substitute the non-serpentine parent types to the appropriate serpentine PFR types. So you can see bottom right, all these purple areas represent serpentine vegetation. Like if it was yellow pine, it converts to serpentine yellow pine, and so on. That's it. We have a new map. This is a comparison between the Kugler map, which is, I haven't talked about it, but it's a potential vegetation map that it was built in the 1960s, and it has been used in several studies, but everyone knows it has a lot of caveats. And in the middle, you see the VPS map, as I was showing at the beginning, some slides before. And in the right part, you see the map resulting from the present study over here. There's huge differences, especially, and you can see in the Central Valley, but also if you look at Southern California and the coast, you could see a lot of grassland vegetation here. And I'm going to have a focus on number one, the numbers you can see here, and number three. Number one is an area north of Eureka, near Orleans, and the left map shows the VPS land fire map, and then the new map that we've built, in which you can see all these more like light green colors representing grasses. And also there are northern slopes, we kept the vegetation tab that the VPS was showing. But for in-between slope, like west and edge, we chose an intermediate successional type. Like for mixed evergreen, We chose oak woodland, or for moist mixed conifer, we chose dry mixed conifer, and so on for east and west light. So that's why you see this pattern over here. Much more heterogeneous than what VPS is mapping. And then for an area around Santa Barbara, in the left side, you see the VPS land fire map. All these brown colors are like chaparral. The dark green is more like mixed evergreen. And then this brownish color is the coastal sage scrub, and then light blue is oak woodland. And then to the right, you see the new map that has a lot of, it still has some chaparral in the bottom valleys, as you can see, like, or coastal sage scrub also in the bottom valleys, if you can kind of deduce a bit the topography here. And then it also keeps mixed evergreen in the northern slopes, but it maps much more grassland types according to the presented methodology. If we look at the numbers, this table shows for each of the Jepson ecoregions at the left and total at the bottom, this percentage surface of grasslands, shrublands, and forests in the columns, but for each type, we show the historic values for the BPS and our map, and also current values. So if we dive into some of the values, we can see that for grasslands in central Western California, our map has a better representation, or has an increased representation of grasses, and it's more similar to what even the FBED shows nowadays. But for Southern California, it also happens there's an increase on the amount of grasslands, but current vegetation is not showing this percentage, but this is mostly because urban areas are settled in grassland areas. So that's why the percentage on current grassland vegetation in SoCal it's much lower than in our map. For shrublands, the Great Valley, Central Valley, you see that VPS was mapping 43% of shrublands in the Central Valley, but with our map, we are having 11%, and even current, again, there's the influence of anthropic land uses, but it's kind of 2%. And finally, if we look at the forest, interestingly, we see that it kind of keeps the same values more or less in the past and in the present, because for instance, here in Sierra Nevada, because this is kind of a more stable vegetation type. Okay, so this is the exercise I wanted to show you about the improvement of a new map for California. And now that we have the vegetation map, we need to know how often did this vegetation burn. And to do so, we have, I'm sure you all know the indicator called fire return intervals, which is the number of years between fires, which is very easy to understand. If we say 13, that means there are usually 13 years between two fires. So to calculate it, you get the number of years, and you divide it between the number of fires. But there's also a very nice statistic that it's calculated using several sources in the same area. It's the fire rotation period, is the number of years needed to burn a region of interest. So the fire rotation, you get the region area and you divide it by the burned area per year, and then it's also in years, and that means that you need, like, if it's a 10, you need 10 years to burn that region area. So if you change this division, you get that the burnt area per year, if you have a region area and you divide it by its fire rotation, you can get an average estimate of the burnt area per year for each ecosystem type. So that's what we did. We got these fire rotation periods from the literature. We know the area in California of each of the different vegetation types, and then we can get an average burnt area per year, the whole state. In terms of the fire rotation periods, there has been a huge effort by my colleagues to integrate different sources of information to get all this data. And also here, there's a lot of integration of indigenous burning information to get these accurate values. The most typical way that I'm sure that most of you have in mind in order to have these values are the fire scars and the dendrochronology, as you can see in the top right here, in which a lot of studies are reporting the frequency of fires in different forest types. But we also need this fire rotation for other vegetation types, such as desert types, shrubland types, or grasslands. And to do it, we took data from different studies that also are providing these values for lake and ocean sediment from sediment cores, and which, according to the chart wall, you can also estimate fire frequencies, and also from oral histories and stories and writings that provide these estimates. As for instance, this picture here, I'm sorry, I'm not including the source, but it's a painting from the Central Valley with a fire. So if we put all this information and values, this is the values that we get. These are in green, you can see the different forest types. Light blue is the grasslands. Yeah, there's oak woodland is here at the bottom. It's in italic because it's like a forest type, but the type of the way it burns, we consider it like a grassland fire more or less. So that's why it's included in the herbaceous group. And then to the right, you can see more of the shrubland types. And if we want to have a look, like the fire rotation period for Central Valley riparian, it's 11 years. For coastal prairies, 6 or 8 years, and for chaparral species is 7 to 2 years. So that's gives you an idea of different like low interval and more like high sorry, the Central Valley was not supposed to be highlighted. It was more like the pinyon juniper 404 here. Different ranges of values for these fire rotation periods. Yeah, sorry, the lowland coastal riparian and alpine vegetation. So when we put all this information together, we get our estimates of burned area in California. And we've been comparing this with other studies and actually also current values. I'm including here some provisional results. We are still kind of refining our analysis, so that's why it's important to know that numbers might change at the end when we will be presenting in a paper. But the present study shows kind of a bit lower values than what other previous studies have shown before, like Scott Stephens' 2007 paper and Martin and Sapsis, in which they have higher estimates for grassland fires, not very much higher estimates for forest fires, but we also get low. I mean, they were estimating higher estimates for shrubland fires, maybe also because of the mapping of the fire in which they were using, or even current maps or the Cochlear map, which overrepresents shrublands according to the different evidence we have. And we can also compare this with the mean burnt area between 1980 and 2023, which, as you can see, it's for forests and grasslands is way below the historical average, but for shrublands it's almost the same. And also we can compare it to the maximum values burned between 1980 and 2023, in which forests they do have an estimate above the historical estimate that we calculated in this paper, in this work, sorry. But then we can also estimate emissions, and to do so we use more like typical Western modern science. So we use a simulator. And this is FUFEM. This is a fire simulator that affects first order fire effects. I models first order fire effects. And you mainly need three information. So what's the like the amount of burnt area burned, what's the fields in each of these units of burnt area or pixels or whatever you have, and then what's the weather like. So the area burned by each vegetation type, I already show how has been calculated. But then we also needed field loadings and weather for calculate emissions. For the field loading, we did an exercise of crosswalking the different fields categories from different sources according to the FUFEM database. We did this average and standard deviation for each of the PFR types. And we always chose the light version. FUFEM has like light, average, or heavy field loads, but because of the frequent burning that we know that was happening before, we chose this light version. We also, it's true that we also needed a percentage ground consumed for forest types, and we used different sources to have these new estimates. And we also included the weather conditions. So to do it, we decided to use the same assumptions that Scott Stephens and colleagues in 2010 did, which is 2/3 of the fires were occurring under dry conditions, and 1/3 was occurring under very dry conditions. So we've been including the same conditions also to compare our estimates with Scott Stephens' estimates. We also included some sources of uncertainty, and we ran 1,000 Fulfin simulations. So this is more like typical uh, simulation analysis that we did, and we got some values. And those, again, are provisional values, and I'm showing here only for certain small components. And you can see here at the bottom the particulate matter 10 and 2.5 for all these different vegetation types. And you can see that most of the emissions come from the forest. Even they don't burn as often or as much as the California as grasslands, they are responsible for the higher emissions, like redwood forest or dry mixed conifer or yellow pine show the higher values of historical smoke emissions in most of the different components of the smoke. And I'm not showing the same graph for dioxide carbon, but we have our estimates for mean carbon dioxide is 6.73 metric tons per acre burn, and whereas modern fires in the last 20 years have emitted 24 metric tons per acre burn. So we had more burned area and more fires in the past, but they were emitting much less than the current fires. We can also put this information in a map according to our historical map, and we can have a mean kilos of CO2 per acre per year, and most of the highest emission values were in NorCal, especially for the forested fires that were occurring in these areas. To finalize, take-home messages. Reproducing historical fire regimes is challenging, as I showed you here, but recent data and method advances provide better estimates, which is good. And here we are presenting a new framework for historical fire regime reconstruction that can actually quantitatively incorporate indigenous culture and burning in the estimation of vegetation type distribution and fire regimes. And we are also happy to show that this approach illustrates how archaeological evidence can be analytically integrated into large-scale quantitative models, and all this information that the reconstruction of historical fire regimes provides insight into long-term processes that can really influence current and future ecological dynamics, I'm sure that you all know. So that's all for today. I also want to acknowledge my colleagues and co-author for this paper, and a lot of people that have been in meetings and questions and answers and discussions. That's it. I'm going to maybe stop sharing. What do you think, Nick? Just to maybe see you better.
Yeah, I mean, you can, if you want to feel free to leave that on or take it off. All that works. We just wanted to say thank you so much, Dr. Wayne, for this amazing conversation. And I was really impressed with your presentation. And I would like to, yeah, open it up for questions. And you have some really great attendance here. I haven't seen any questions being posed in the chat just yet. So everyone feel free if you would like to just submit those in there. And I had one that we can start off with, but I was just really yeah, curious about this collection of like historical and traditional indigenous knowledge that you were able to gather. It was really impressive. And I'm wondering how like especially when you were first starting this project, like how this approach for integrating all this archaeological evidence into these like large scale quantitative models, like working with you mentioned like the San Francisco Estuary Institute and the Central Valley maps, these diaries, these newspapers, and then the phytolith data, and then feeding that into like machine learning models and trying to get like this spatial sphere of influence. Uh, I just was wondering like what was like the hardest part of that translation from all this qualitative historical data to this quantitative framework that you've built.
Yeah, so I'm more like a data person and I like a spatial person. So in this case, it was kind of easy for me to know that everything I wanted to do needed to be spatial. Like as I showed before, like the indigenous impact on vegetation, we knew that this impact was there because of all the evidence we have. But relying on the location of villages was super inspiring for us in order to have a way to include these impacts. And even we know that villages were not stable, they were changing on time, and maybe that the impact of this management was not especially or only around the area. Maybe in some areas the impact was more in some slopes, but this was a way that we could incorporate this information in a spatial map that could be assessed and quantified. And that was super important to me to know that we could do this in such a way that could have, as I said, an impact on a map. And then maybe the most challenging part for me, because I'm not an archaeologist, was actually to find all the information because it's out there, but you don't always have the time, or you don't know where to look at, or the specific sources. So in this case, talking to a lot of people, um, of course, looking at the internet, but also consulting colleagues or people who know a lot about, like, especially our co-authors, Don Hankins and Frank Lake, which are from the indigenous community, and they know very well where this information comes and what are like good sources of information as well. So that was super helpful. Without that, we couldn't have done an exercise like this here.
Thank you so much for that really thoughtful question and answer. I also wanted to make sure that we were able to ask you one of the questions that we're asking all the presenters of these sessions, and it's how can people from different fire backgrounds, scientists, policymakers, indigenous practitioners, community members work together to shape the future of fire ecology? And a follow-up with that was also, is there one fire-related misconception that you also find that the public remains to be struggling with? And how can we address that collectively?
Okay, for the first question, how can we work together? I mean, I think that the first way to start with is like finding common spaces for conversation. And everyone is super overwhelmed with their own life, and we all have a lot of delivers to present and talks and classes, and it's really difficult to find moments. So I'm happy to see that conferences like the last AFI conference in New Orleans, we saw that it was not only about Western science. There was a lot of interaction between different fields and profiles and backgrounds, and that is happening nowadays. And this is one of the best ways that both like typical Western science or other fields can feed each other to build together. And if this is not happening in these important meetings, then it's difficult to happen because, as I said, we don't have maybe the time, or it's difficult to find a moment to make this effort to go to an area where you don't feel very comfortable. So it's like that this is happening, and we all make a bit efforts. And also in this presentation, I also showed methods to try to mix different approaches. Regarding the fire-related misconception that the public remains to be struggling with, I would say two, actually. I would say that's the more typical public that is super unaware of fire ecology would say that fire still has a very negative impact on ecosystems. So I guess that's here we need to work, the scientists and managers need to work towards providing more information, and also in a way that it's transferable for society. So if we know that fire increases native species richness, this needs to go into media. We need to explain this better. And we need like infographies. We need ways that this reach the general public in such a way that it's easy and it's not just in a scientific paper. So there's work here, and there's a lot of need to still translating all the amazing science that is being done into this more general media and the general public. But the other misconception I would say is that for the people who are aware of more like the typical historical fire influence on vegetation, we are hearing maybe too often that we need more management of every type of vegetation. And here I would say that maybe it's not easy to explain that grasslands and shrublands don't need the same management as forests. And the big fires that are having huge impacts on urban areas and human societies are sometimes related to these other more grasslands and shrubland types than forests. So there's kind of also we need to explain well what it needs to be done in order to reduce the negative impacts of fires occurring in these vegetation times. And maybe it's not just um, going to say we need more management here, but also we need to protect ourselves and we need to be more aware of the risk of fire in these areas. So I think that there's also path here and way to improve the way that scientists and managers communicate with the general public.
Amazing. Thank you for answering those questions. And that actually bleeds into one of the Q&A questions that Juan Pablo posed. He asked, in a nutshell, for communicating to the layperson, how did more fires and more area burned result in less carbon emissions?
It's this is a question from the chat. Sorry, I'm not seeing it. I'm not sure if I'm seeing the questions. Yeah, this
If you
is
click on
mostly
Q&A at the bottom, it might pop up for you. It's
okay.
different than just the chat. Yeah.
Okay, I don't have this bottom. I only because I'm a panelist and maybe I'm not only seeing the chat, but it's okay.
Okay.
Why we have less emissions if we had more burnt area? This is mostly because the type of fire. So if you remind my slide, grasslands vegetation time had almost no particulate matter emissions in even considering the whole amount of burnt area in grassland times, which is like 800,000 hectares a year. So this also has a huge impact on carbon emissions. And then if you look at the type of fires that were burning historically, in forest types, they were burning mostly the understory and not the canopies and the trees. That's why we see more burnt area, but not as high emissions as we see nowadays, where fires are burning mostly forest areas and burning the whole vegetation vertical structure, including canopies and the trees. So that's the main reason behind the difference in emissions between present emissions and historical emissions. So from this, actually, one lesson to learn would be like maybe having more fire is more positives to the total carbon uh, balance. And sorry, I forgot what I was going to say. Yeah, having more fire. Yeah, so we shouldn't be focusing as much on burnt area as an indicator here, but more on what are the impacts of these fires as a way to make decisions.
Beautiful. And also another question that Neil posed that I'm sure we all have is your map available and where will that exist?
It will be available hopefully soon when we publish all this work. Yeah, it will be for sure in a public repository. That will be for sure. I'm also looking forward for people to use it.
Amazing, beautiful. Another question that one of our participants, Marcos, had was, how did you control the vertical mobility of the burnt materials and the sampled sediments to estimate the real depth and not overestimate it or underestimate it? I'll also put it in the chat.
Yeah, so I think that the studies are providing estimates of, I mean, I'm not the expert on the paleological part. I'm just like interpreting the information. But what I read is that these studies are using information, for instance, in so-called as ocean cores. And usually historical fires in these areas, I'm sure you all know, were driven by strong Santana wind events. And all these winds were pushing all the ashes towards the ocean. So in these areas, for instance, it's kind of easy to relate the charcoal that was arriving to these sites in the ocean to the fires that were occurring in the coast because of the nature of the wind direction of these events. So in this case, it's an easy answer because it's kind of related. In other places, I'm sure it's more challenging. Um, Very likely researchers are using several sites to answer this question and just not using one, but several different areas in order to know if that core is representing the vegetation surrounding it.
Okay, lovely. I think we're nearing on to our last questions, but Corey posed one that I thought was really interesting was given what you learned about improving the BPS map in California, what advice would you give to the Landfire program to improve the BPS map nationwide?
It's difficult. It's difficult because the methodology behind the VPS is robust. But what happens is that it's based on current plots, and current plots are representing current vegetation, which is a result of already 100 years of fire exclusion. So it's not representing actually current plots of historical conditions. So it actually cannot represent like what I was happening before the Euroamerican settlement in areas where um, people were like very densely settled in some areas, like in California. What we know is in other regions, and for instance, southeastern US have also done this exercise of improving the VPS. So we are not actually the first ones doing it. And they found that in their area, VPS was also underrepresenting grasses. So I would say, not sure what the methodology should be for the VPS, like if you need to always overlap historical maps or not, if you need to have village maps for everywhere in the United States, which I'm sure is not possible, but at least like kind of having an acknowledgement that this map maybe represents kind of late successional vegetation stages, and that in many cases might not be actually representing historical vegetation because it is not. And just as a small quote, we already have had some meetings with them, and it's very difficult to try to improve the VPS at the whole county and state.
Wonderful. Thank you. I think unfortunately we have more questions, but we don't have that much time. So we'll save them, Andrea, and send them over to you. But as we wrap up today's session, I just want to thank all of you guys for joining us. And a special thanks to Dr. Dwayne for this really amazing presentation. And to say that our next section will be January 28th at 11 a.m., where we'll be discussing extreme wildfire ecology, lessons learned for integrated fire management with Mark Castano.
Okay, thank you very much, Nick, and thank you everyone for also engaging and participating.